So we're going to talk about infrastructure as code and apply it to serverless compute. First, I have to define the infrastructure. So you came here for the conference. You probably know what serverless functions are. That's a piece of code that you put into the cloud, and then it runs every time an event happens. But it doesn't exist in isolation. In order for it to work, you need some other services to run it. So you need to put your code into the bucket. You need to integrate with HTTP endpoints via API gateways and so on. You probably do some async processing, so you need queues and event streams. And you also need to store your data somewhere because serverless functions are stateless. If you dig deeper, you can find more infrastructure like login, monitoring, security. You also need to make orchestrations of your functions. You need to connect functions to some third-party services and whatnot. So you have a lot of components to manage in order to complete your application, which might use serverless functions. So that's the infrastructure that I'm going to tell you about and that I'm going to manage with the code today. I come mostly from Azure background, so that's what I know best, but probably a lot of you might have AWS background, so I tried to mix both in my slides, so I use them quite interchangeably. Hopefully everyone will be able to pick up some examples and understand what I'm talking about. And for the rest of my talk, I go through several tools. It's going to be quite high level. I compare them together. I identify what you should be looking at while choosing the tool for your job. So let's just start. I'll use a simple example, a URL shortener, so something like a bit.ly or tinyurl.com, very simple. You define some short codes for long URLs, and then somebody goes to your website with this short code, you would redirect them to a full URL. This example is good mostly because for any technology that you can pick, you go online, you Google for URL shortener plus that technology, and you find an example implementation. So it's really easy to find those and compare them to each other. That's what I did. So if I were to use AWS Lambda to implement URL shortener, I would probably do it like this. So I have a DynamoDB table where I store the mappings from short to long URLs. And then maybe I have a couple lambdas. One lambda adds new URLs, so it takes an HTTP request, gets the information from it, puts it into the table. And then the second lambda is listening for my short URLs, extracts the code from the URL, looks up the full URL, and then makes a redirect. Okay, that's really easy. It's like 20 lines of JavaScript to implement this application and get going. But resource-wise, it's not the complete story. Of course, Lambda doesn't have integration with HTTP out of the box, so you have to use API gateway for this. You also probably have to provide some front-end side to add new URLs. You need an S3 bucket to put HTML assets in there. And if we dig deeper, every resource requires some additional configuration. So AWS API gateway needs stages, deployments, endpoints. You have to configure security, IAM roles, policies, maybe networking, maybe some DNS, CDN, and so on. So it's easy to see how you come from 20 lines of JavaScript code to 20 other resources in AWS that you have to provision in order to make this application work. An example from Azure, generally Azure resources tend to be like a bit higher level than AWS ones, I think. So it's not that many parts to manage there. But let's just take a look at the target scenario when probably you expect users from all over the world, so like from America and Europe and Africa or whatnot. And to provide the best experience for everyone, you probably want to create a globally distributed application. So in Azure, I could use Cosmos DB for this, so create several replicas in every target region. But then my functions, cloud functions, are still local to one region. So I have to create several copies of the application, put them into the same region where I have my Cosmos DB, and then have some front-end routing service like traffic manager or front door, which would direct traffic from end users to the nearest location in Azure. So again, you can see like I get to create a dozen or a couple dozen resources, depending on the amount of regions. And it looks quite repetitive and actually boring to do it correctly. Also, there are a number of places where you can misconfigure it. For example, replicate Cosmos DB data to the region where you don't have function app, or configure a function app to connect to the wrong region, or misconfigure traffic manager. So the mistakes can happen here. So how do we actually create this application? That's the question for the rest of my talk. The default answer is that you go to the portal and you start clicking. So my first advice, never do this for any application which is supposed to be sort of production-like, right? You can play with it for the first time. It's good for discovery, for exploration. They cut the corners, make it as easy as possible, as simple as possible. But once you're done with this, you should probably switch to some automation tools and use portals and consoles just in read-only mode to see what actually happens if you need to. And the main reason for this is that whatever you do today, you're not going to be to reproduce this next week. Or even worse, your colleague will not be able to do this in a couple months. Every deployment will be different in subtle ways, maybe even if you write a guide or something. But still, you're not going to be creating reliable deployments with manual clicking. So instead, you want to use infrastructure as code. And I use this term broadly. So anything which is not clicking in the portal or interactive CLI is infrastructure as code. Basically, you define a piece of text, so textual file, a code or markup, and then there is a tool which knows how to read this markup or code and create infrastructure out of your definition. It gives you a number of benefits. First, of course, repeatability, so you can reproduce the same deployment as many times as you want for multiple environments or multiple projects. It also gives you great documentation, so it's always up-to-date documentation because it describes exactly what infrastructure you have. You can put this code to Git. You can check the history of changes, why you changed something, when did it happen, who did this. And because of those repeatable and reliable and safe ways to deploy, you tend to make changes more often, rely on them more, be comfortable with changing things at higher pace, innovate faster. Also, you can, if you have a problem which probably somebody already solved, you can always find an example of code and then reuse it in your setup, or you can share your code with your colleagues, and if a different team solves more or less the same problem, then you can reuse your work for other solutions. And last but not least, having control over infrastructure makes people happy. So when you trust your tools, you are more satisfied with your job. And I think many people underestimate this. When you choose a tool, you should feel comfortable working with it. If you don't like the tool, you're not going to use it to the full extent. You're not going to embrace it. So when you go through the process of selection of tools, always just ask yourself, am I satisfied with what I get? The need for automation was realized a long time before by all cloud providers. So every cloud provides the basis for automation. This example is from Azure, but all other clouds are the same. Basically, there is one huge management API layer where every service managed by the cloud provider can be created, instantiated, deleted, and so on. So it doesn't matter how you create a new service, a new Lambda, or a new S3 bucket, or in this case, web application in Azure. You always have to go through this API. So all SDKs, all CLIs, even the web console talks in the end to this API layer to create new services. On the lowest possible layer, you could do the same. You could just talk directly to that API with HTTP requests, and sometimes maybe you have to do this, but it's very low level. It's very not friendly to develop like this. So there are multiple ways to abstract it away. The first, every cloud provider has an SDK for most common languages, where basically the code from C# or Java or Python would be translated to those HTTP queries that I showed on the last slide, one-to-one, more or less. But you get strong type and you get compile type checks and IntelliSense and whatnot. And also there are CLIs, so command line interfaces, tools that build on top of those APIs and provide you automation capabilities. So that's one style of infrastructure as code. You can just write bash scripts or PowerShell scripts that call out to CLIs and then create resources one by one. This works, but it has some challenges with it. First, this is very imperative, so you have to exactly describe step by step what has to be done one by one in the exact order. This may be fine for the initial deployment, but when you have multiple environments and they're all in different states, and you need to update your environment from current state to new state, you kind of start to write update scripts, and every environment is a little bit different, so it's hard to make it reliable enough and error prone. It's just a lot of labor. Also, if your script fails in the middle, you sort of don't know where it failed and like what's the current state of your infrastructure. So that's another problem that you have to handle. Usually, scripts are fine for smaller projects, but if you live with them long enough, you start to kind of reinvent the workflows of other tools that I'm going to describe later. So probably I would not recommend this for large projects. Instead, what the industry came to is the approach called as desired state configuration. The essence is that you have to describe your target state, so what you want to get in the end. And then the tool takes care of applying this target state to the current state of your environment and bringing it from the current state to where you want it to be. So it doesn't matter if you did not apply your patch yesterday to production, but you applied it to staging environment. If you run the same target state, they should come to the same configuration. If we zoom in a little bit, both target and current state sort of describe the graphs of resources. So you have resources which are nodes in these graphs, and errors are like dependencies between resources. So your tool has to be good in two ways. One, it should be expressive enough to describe the graph exactly as you want it to describe. And second, it should be able to take any current state and any description of the target graph and morph the current state, apply all the required changes so that they do not diverge, so that they look the same. And this looks pretty simple, but there is a number of challenges with these tools. So how do you understand what are the dependencies in your graph? Do you catch all the relationships between different resources? We move more and more towards immutable infrastructure. If you change something important about the resource, it's easier to create a new one instead of changing the old one. And then, again, the question, if there are other resources depending on this one, how do you replace the resource in a reliable way? Do you create a new one first and then change all the other dependencies? Do you have to kill the old one first? And so on. Ideally, you want to do this with zero-time downtimes, right? You don't want your users to notice that you are applying upgrades to infrastructure, so that's another challenge. Also, because you can make mistakes in your plan description and your target state, and also the tools might not interpret it the way you expect them to interpret. Ideally, you should see the plan before it's being applied. So there should be a preview phase where you see, given this target and current state, what are the steps that the tool is going to execute. Drift detection is about when somebody goes to the portal, for example, and changes your resource, which was managed by a tool automatically. can we detect this, and can we reconcile the changes that somebody did with the target configuration? And of course, still we have our error handling problem. If deployment fails, what do we do now? Do we start to roll back to the last known good state? Or do we make the user fix the issue and roll forward again, try to reconcile again? If we roll back, what do we do if rollback fails? Like all that kind of possibilities. So these are the things to keep in mind while evaluating tools. So every cloud has their own desired state configuration tool. CloudFormation, Azure Resource Manager, Google Deployment Manager. They're sort of similar on high level, but of course different in details. So Azure ARM templates, they use JSON to define infrastructure. You write a big chunk of JSON with a node called the resources and then a flat list of resources. And then you define dependencies in the JSON values. And mostly what this tool does, it converts this definition of resources in JSON almost one-to-one to HTTP calls. So it takes the properties and then puts it in the body and sends it over. And the other nice feature that you get from ARM templates is that the deployment is managed by the cloud itself. So you send your large JSON to the cloud, and then it will run it as one unit of deployment. It will show you the history of those deployments. It will show you the failures, which resources were affected, and so on and so forth. So you don't have to run it from your own client machine. AWS CloudFormation is somewhat similar. They also started with JSON. I think now YAML is the most used language, but it's still the same. You define resources in a large configuration file. There are constructs on top of YAML to define things like dependencies and some primitive conditions. And then you send it to AWS, and AWS deploys your template and creates resources. If I compare CloudFormation to ARM templates, it has some nice features. Azure ARM is very bad with previewing changes, and it's hard to understand what it's going to do before you actually run the deployment. CloudFormation has change set, which is being able to compare your target configuration with your previous configuration, and drift detection, which is give me the diff of target configuration versus current cloud configuration, right? In case something changes. It also tries to automatically roll back if something fails in the middle. This is not perfect, but it's a neat feature. Yet, all the tools from the cloud vendors, they have some limitations. Of course, first limitation is that they are specific to that one cloud. So if you know ARM templates, you're not going to reuse any of your skills pretty much if you go to AWS land and vice versa. Also, because they are so fundamental services of the clouds and they cannot make breaking changes and they have to support all the services, they are sort of rigid and low level, so things work the way they work and they don't change that often. If you don't like it, you cannot do much about this. It's all closed services, so you cannot see the source code, you cannot contribute. You can only complain and hope you'll get something back. So yeah, pros and cons in this case. There are other options as well. So Terraform is one of those. Terraform is made by HashiCorp, so third party, not related to any specific cloud. And they decided to reinvent the whole pipeline of infrastructure as code and created everything on their own. So they have their own language to describe infrastructure, which is called HashiCorp configuration language. And they keep evolving this language quite fast pace. They just changed it like this year to version 2.0. And it sort of looks like JSON, I don't know, because of curly braces. But it actually, in practice, it's much more lightweight. So you don't have large trees of inline resources. It's very flat. the references from one resource to the other resource look like this. So you have resource group name pointing to resource group by the type and the name and the property. And that is enough for Terraform to derive dependencies between resources. So it's quite neat. It's also multi-provider, so the Terraform core engine doesn't care or doesn't know about AWS or Azure. It knows about the resources, the properties, and the graphs and dependencies. So it builds an abstract tree first, and then it calculates how to bring the current state to the target state in terms of that tree of resources. And then it calls the providers, what they call providers, for CRUD operation, create, update, delete operations. And those providers are specific to the cloud, and there are like literally hundreds of them. It's not just AWS, Azure, GCP, it's also not really cloud, things like HashiCorp Vault or Postgres on monitoring tool like New Relic. You can also create your own providers because it's all open source. So the vision is that you manage all your infrastructure, even if you are multi-cloud or if you are one cloud but you use other tools, maybe something like Kafka or whatnot. You can manage all the infrastructure from one stack of Terraform. So if we look at the breakdown of layers, you write your program in HCL on the top layer. Then there is a CLI, Terraform CLI, which drives everything. So that's a difference to cloud tools. The deployment doesn't run in the cloud. It runs on your client machine or in your CI/CD server, but it's a Terraform CLI which drives the process. It builds a tree of resources. It compares to the state. It produces the plan to go, and then it calls out to providers. In this case, in this example, to Azure provider, please create this resource. And then Azure provider calls to Azure Go SDK, and in the end, it all ends down with ARM resource, Azure Resource Manager. One downside here is that a cloud feature might be not supported in Azure Go SDK. It might be not supported in Azure Terraform provider. In this case, you are sort of out of luck. You have to fall back to some other tools. So you don't get automatically 100% feature coverage. Somebody has to go to Terraform and actually implement, do the work of writing the calls to ARM for you. It's open source, a lot of contributors, but still for smaller features or newer features, you might not get the coverage from Terraform. Terraform also has its own workflow, a good one, I think. So there is a command for plan, where you get to see the preview of what changes are about to happen. It's very detailed. It shows every property. You kind of have to get used to navigating it properly. But then you can see exactly what's going to happen when you actually run it. And then if you're happy with this, you run Terraform apply, and then the deployment starts. And if you don't need your infrastructure anymore, you can do Terraform destroy, which is very good for experimentation. If you ever created a bunch of AWS resources and then try to delete all of them to the clean state, like, you will appreciate Terraform destroy, which does this in several seconds or minutes. So Terraform plan, as I said, gives you the printout of what's going to happen. And it also handles replacement. So if a property change makes the resource to replace, you will see this in red in your CLI, so you can evaluate if that's what you actually want or not, and either change your configuration or apply. There are actually 2 sessions this afternoon related to Terraform, so if you want to learn more, go to one or both of these sessions later. For now, I'd like to emphasize on one problem here. So I found examples for each tool for my URL shortener. And my function code is about 20 lines of code. But for any of those tools, the code that I need to provision my infrastructure is like order of magnitude more. And this scales more or less linearly. The more functions you have, the more dependencies you have, the larger infrastructure you have. So we badly need some higher level abstractions here to reduce the burden of defining infrastructure. How do we create these abstractions? How do we compose our applications from these abstractions? How can we reuse these components? And how do we still make sure that applications work the way we expect them to work? So there are two approaches here to this problem. Basically, you can use specialized tools for this, which already provide you these abstractions, or the tool can enable you to write those abstractions on your own. So serverless framework is one example of domain-specific tool. So it focuses on serverless applications, right? There is SAM from AWS, which is kind of similar. Serverless is multi-provider. It exists for several years. And it's still YAML that you write here, but the primitives are more high level. So you define it in terms of functions and triggers and dependent services. And then all the low level stuff is kind of taken care of by the tool. So the experience of getting started is very good. It's very easy to start. Just take an example. You understand what you're doing. It just works. It also is multi-cloud. Based on my experience, when I tried it for Azure, it wasn't great. I think AWS support is still much better. But I've heard that they improved. I cannot confirm that. But it's, as Terraform, it's multi-cloud by design. But sort of applicability is limited. That's a bigger issue to me. If you start doing not just serverless applications, or like you start bringing other services into the picture, you have to be ready to fall back to other tools like CloudFormation or Terraform. And that means that you need to use two tools and you need to learn two tools, and that's just not very compelling to me. So the other path for making abstractions is to build the creation of abstraction, the first-class citizen in the tool itself. So one tool which does that good, in my opinion, is called Pulumi. You can think of it as Terraform, but the major difference is that you can use general-purpose programming languages to define the infrastructure. So like JavaScript, Python, Go, C#. Here is a basic example of TypeScript resource. So you open your Visual Studio Code or something, and then you type new object. You create a new object, and that defines your cloud resource. So if I were to create my URL shortener, I basically need three resources. The first block defines a DynamoDB table. The second block defines a Lambda function. Notice that I'm using the DynamoDB table in the function definition, and that creates the dependency graph. And then the last node is API gateway to bring HTTP support here. And again, it's using Lambda as an input for definition. And you can see it's quite high level because I'm using the high level components there, but they are all coded in the language itself. So I can always drill down to details and define all the nitty-gritty of IAM policies and so on. But I can also use high level components which take some sensible defaults here. The important thing about languages is to understand that this is still described in the desired state. So when this program runs, it doesn't mean that every new enough of a resource goes to AWS API and creates a resource at that point. It actually builds the graph of resources and it doesn't do anything else. So maybe I can illustrate this with that diagram. So the bottom part, language host, runs the program and creates resources from TypeScript or Python or C#. And then it gives this tree to the engine, which is like Terraform from that point. It gets the tree of resources, it calculates the difference between current state and the desired state, and then it delegates to providers to actually do the work. So I still define resources as a desired state. I don't have to write migration scripts, but I do it with the languages. It's multi-provider, so AWS, Azure, GCP, whatnot. You can also plug any Terraform provider to Pulumi provider, and then it will just work. And if you're a developer, the tooling is very natural. You just use the same IDEs. You get things like auto-completion when you type. You get compile errors if you are missing a property or you made a typo or something like that. You can use conditionals, loops. In this example, I go through the list of locations and create a function app for every location. It's just a loop in JavaScript. And I can use things like string interpolation, for example, in this case. But the most powerful thing is that I can create my own components if I want to. Here I created an AKS cluster, not very serverless example, but still. And it creates a bunch of components inside, which the client of this component shouldn't really know about. And that's where I need all the conditionals, all the loops, all the power of a general purpose programming language, because defining a component to be flexible and suitable most certainly requires you to bake some logic in it. So Pulumi is not the only one which brings general purpose languages to the infrastructure. AWS has their own cloud development kit, CDK, which I think was just released 1.0 not that long time ago. And the idea is similar, that you use TypeScript, Python, Java, .NET to define your infrastructure, the desired state of your infrastructure. But the implementation is a bit different. It compiles or transpiles down to CloudFormation templates. And then you get the rest of the tooling from AWS with CloudFormation. So the deployment is the same, has the same properties as CloudFormation, which is good and bad at the same time. You get all the features, you get all the problems as well. But the code looks very much like the previous example that I showed. You create a new function, and that's a variable in your program, and then you can refer this variable in other resource definitions, and thus define the trees. So if you want to know more about CDK, we have Richard Boyd from AWS right there. I'm not sure if your session is going to touch on CDK or not, but you can talk to Richard in like lunchtime or something, and he will explain you all about CDK, I believe. So the bigger intention here, I think, for me, I borrowed this term from a blog post by Claire, that we move in from infrastructure as code to architecture as code. We can reason on higher level of abstractions, or actually on the level of abstraction that we want to. So let's say you draw a diagram like this. I have a timer, and I want to execute every 10 minutes a container in ECS cluster. And then your code can look very much like your diagram. You create a new resource, and you have a schedule of every 1 minute, and then you have a container to run every 1 minute. So it's the same level of reasoning. This picture and this code, you can go from one to the other. Different example, you have two buckets. Every time you get a report in the first bucket, you want to run the Lambda, zip it up, do some preprocessing, and put it into a different bucket. Like you probably did something like this many, many times in your serverless applications. So you can write the code which should look more or less the same, should have the same structure. So first you create two buckets, that's just two objects, and then you can use, this is actually a Pulumi example, you can use just a callback like we would do in your Node.js application or front-end application. You can say bucket on object created and then give it a callback where you take the incoming document, you preprocess it, you zip it up, and you send it to the output bucket. And then it's the responsibility of the tool to take this code, to package it correctly, to zip it up, to put it into AWS, instruct it to run the Lambda properly, and so on. But you think on this level, and then you immediately go from this level, from your architecture diagram to the implementation, like this. And you can also do these abstractions on your own. So on the example I gave in the beginning, that multi-region, globally distributed application. So I'm using Azure Functions for this. I put a function app in every region next to Cosmos DB table, and then I create a traffic manager with endpoints for every region, maybe my colleague is working on a different microservices in the same project, and they want to use something different than functions. They want to use containers or virtual machines to do some processing. But they still might want to the rest of my infrastructure. Like they still want globally distributed Cosmos DB. They still want to deploy to multiple regions. They still need to route their traffic from the website. So what I can suggest to them is that I could create an abstract component which does everything except the compute layer. And once we agree on this, and once we implement this, then my application can look like a simple block of code here. So I instantiate an instance of my component, Cosmos app, and I give it a list of locations to deploy my infrastructure to. And then I just pass it a factory, because we are in general purpose programming language. I can just pass a function there, and that callback is going to be called for every region, once per every region, and it gets a location. So it creates a function app in the location, and it returns, it connects to Cosmos DB, and it returns the ID of that function app. And all the other wiring, all the front end, all the back end, all the Cosmos DB is done by my component, but I still can plug containers here if I want. I can plug a Kubernetes cluster, a virtual machine scale set, or whatnot. And that, if that's what makes sense for our project, for our teams, then we can share this component and work on it together while still keeping our differences. So I think that's the main power of using general purpose programming languages for infrastructure. Some people are sort of averse to this, like if you're gonna give your full power of programming language, you're gonna shoot yourself in the foot and like blow everything up. Especially operations people don't feel very well about this. But yeah, I guess we still to learn whether that's a good thing or not, but I kind of doubt that the argument of not giving your developers enough power is a good one. I probably want to have good policies in place, get guardrails around what developers want to do or can do in your environment. But even if you give them tools with lower power, they're still gonna find the boundaries and like do wrong things. So I would say they can use whatever tool they like, but still just put them into the proper environment to make sure they don't do bad stuff. So to wrap it up, what are the conclusions? So the first one is, if you are working on cloud applications, which I assume everyone in this room does, please don't click your applications in the portal. Use some sort of infrastructure as code. Pick the tool that you like most or you dislike the least, and use that tool to automate all the provisioning and deployments. There is no perfect tool. It's always depending on your context. You can choose between procedural scripts versus declarative desired state. The tool can run on your cloud machine like Terraform versus being deployed from the cloud itself. We discussed all the different code formats and languages. Pick the one that you like. It can be a single cloud or provider-based with multiple clouds and multiple pluggable tools. Feature coverage may vary, so if you're really using a lot of features, maybe a native tool is going to work better. And of course, an important factor is maturity and ecosystem, whether you can find examples, documentation, whether it's stable, whether it works as advertised, and so on and so forth. On a higher level, I think we see the progression of components becoming smaller and smaller, so from hardware to virtual machines to the containers, microservices, serverless functions. And the smaller components you get, the better tools you need to manage them, because you get more of them. And then the better tools you get, the smaller you start to make your components to be more flexible and more abstract in a sense. And the more sophisticated combinations of those components you start to use. So I think we are in this cycle of one side causes the other to improve, and the other improvement causes the first side to go further. I think we are just in the beginning of this path, or in the middle of it, so it's an exciting time to get into infrastructure as code. I believe the tools that we use today will not be the same in like 3 years or 5 years. So a lot to learn, a lot to master, and a lot to grow with. And with this, I think it's almost lunchtime, so thank you, and see you later.